Good afternoon, everyone. Today I would like to introduce something in section B, which is a section of heat and thermodynamics. And I would like to introduce what we call heat transfer. So we are having what we call heat transfer. Heat transfer is basically just the transfer of heat. But how do we transfer heat? According to the laws of heat transfer and thermodynamics. From all levels, we have some methods of heat transfer, among which we include one, conduction, we have radiation, we have convection. All those different types of heat transfers, we are going to talk about them in this area. And then starting with, we are going to look at what we call conduction. Then we are introducing conduction. Remind me to send you notes so that you can make better write-ups. Next week, we are going to have a test having all the three sections. Those of you who just joined later, after we had begun, I sent some videos which you can visit on YouTube and check them out. You can download them so that you can be comfortable. At any one time, you have them. So today we are starting with what we call conduction. And the conduction, basically the transfer of heat energy from one place to another through a substance without moving the substance itself. What does that mean? If I have this device and I want to transfer heat from this end to this end, and this device is not in motion, here it's moving. If it moves to gain heat, then it is not conduction. But if the heat moves from this edge comfortably to this other edge, without this keyboard, this white board moving, though it's black, without this board moving, then we say the board is under what we call conduction. Okay? So by definition, we can say this is the transfer of the heat energy from one place to another through a substance without movement of the substance as a whole. If you have ever been close to a stove, a cooking stove, which you call the one you call a sigil, or you've been to a fireplace and you're seated there stationed, you're not moving. By the end of the day, you start feeling heat from your feet to your legs to wherever you're feeling the heat along the body. Then your body is conducting heat in that way from the stove. So you are transferring heat while you are not moving as you. So we have what we call the mechanism. The mechanism of heat conduction. How does heat get conducted? How does this occur? What exactly happens? Yeah. So, for example, we can talk about a specimen of a material. If it is heated at one end, yeah, it gains what we call thermal energy. The molecules on that side will gain what we call thermal energy, and their vibration will increase. You know, for molecules of solids, because basically here we are looking at a solid. If a solid has particles which are oscillating about fixed positions, they are not in motion, While for a liquid, it has molecules which are in motion, though slowly. Then in gases, they are in random motion, but faster. So for a solid, the molecules are fixed about given positions. So when you increase their energy by heating the solid, they increase their rate of vibration about those fixed points. Okay? So that's why I'm saying that once a specimen or material has been heated, yeah, once it has been heated at one end, it gains thermal energy, or there is an increase in thermal energy. And therefore, there is an increase in vibration of the molecules about their fixed what? Position. So this energy can be passed on to other molecules. What happens is, if this molecule is here, look at my fingers, this molecule is here, another one is here, another one is there. They have all been vibrating about the same fixed position. Then when this one vibrates faster, it will exchange energy by collision with this next one. Then also this one exchanges energy by collision with this one. Then also this one exchanges energy by collision with this other one. So the process will go on continuing until you reach the edge of the material or the substance you're dealing with. So you can further say that this energy can be passed to other atoms by intermolecular or by interatomic vibrations. Now, this conduction can basically be best explained when using metals. In metals, we have what we call free mobile electrons. So every metal has got what we call free mobile electrons, and these free mobile electrons, they are in what we call thermal equilibrium with the surrounding atoms. If they are in thermal equilibrium with the surrounding atoms, it means, one, the electrons in atoms, as we shall talk about atoms in modern physics, electrons are in continuous random motion. And if they are free in metals, then they are moving in certain allowed orbits called energy levels. So as they move there, they are in thermodynamic equilibrium in a way that if the atom is not heated yet, the electrons will stay where they are until when the metal is heated. When the metal is heated, it means its atoms have got heated. When those atoms have got heated, we shall end up giving an electron thermal energy or more kinetic energy. So these electrons will start moving further and faster away from the positions where they were before. But before being heated, they are in what we are calling thermodynamic what? Equilibrium. So with the surrounding atoms, so these electrons travel at high speeds and transfer vast amounts of energy from one part of the metal to another by collisions with their electrons and atoms, or with their neighboring electrons and atoms. That is what I've mentioned about electrons. That because metals have free mobile electrons, when we heat a metal, the electrons gain kinetic energy. And when these electrons gain kinetic energy, they are going to move faster and with a vast amount of energy, or with a big amount of kinetic energy. So as they are moving, they are going to make collisions with the fellow electrons they will meet on the way. They will also make collisions with more atoms of the metal. And with that, they will be exchanging some of their energy to those electrons they have met and to those atoms they are going to collide with. Therefore, this means that in metals, heat is carried by two mechanisms, mainly or majorly by one, motion of the electrons. So in metals, specifically, heat conduction is due to motion of the electrons, which when given kinetic energy, they move faster and collide with other atoms of the metal. Thus, they would be exchanging what? Energy. Then the second method of heat conduction in metals is what we are calling the interatomic vibrations. The interatomic vibrations, we have talked about them earlier. They come as a result of the fixed atoms of solids, which are vibrating about the same fixed position. And when they are increased in energy by gaining heat, they exchange the energy to the nearby what? Atoms. Now, we shall also look at what we call conduction of heat in non-metals. That was basically in metals and other solids. But we have items which are not metals. So if we have an item which is not a metal, what will happen is also this item can be in position to conduct heat. Yeah? Haven't you seen items which conduct heat? For example, our bodies. Our bodies have heat. You see, there is always a temperature gun they put on us to measure our temperature. But if they have found you when you have been close to a stove, your temperature will not be between 35 to 37. It could be something slightly bigger than that. It means your body has also conducted heat, but your body is not a metal. It's a non-what? It's a non-metal. So in non-metals and liquids, the molecules are coupled together by intermolecular forces of attraction. So molecules of these non-metals have intermolecular forces of attraction that keep them together. Yeah, there are virtually no free mobile electrons. So in this case, you don't have any free mobile electrons that are just moving on randomly in a non-what? Non-metal. And therefore, in this case, heat is transferred from one atom to another by the interatomic vibrations. Yeah, because of the vibrations of the atoms, we shall have heat being what? Transferred. This process of heat conduction is slow compared to that one of metals. So it means that in non-metals, that's why when you have a non-metal, non-metals are not good conductors of heat. I think you've always heard that from primary. That non-metals are not good conductors of heat. Reason being, it's because they are slow. The method of which they are using to conduct it is slower than the method which the metals use. The method which the metals use is faster. So making non-metals become bad conductors of heat. We do not say that they do not conduct, but we just say they are bad conductors of heat. Then the other thing also I should mention out of this is that the reason why the metals are better, it's because for them we have said they conduct heat as a result of basically mainly due to free mobile what? Electrons. So metals, the difference between metals and non-metals in their conduction, metals have what we call free mobile electrons, while non-metals have no free mobile electrons. So heat transfer here is slower, while heat transfer here is faster. Let me hope this rain won't interfere my sound. Can you still hear me? Yeah, I'm going to send the write-up of this explanation on the group. For those of us who are new and you're not yet on the group, please you let me know so that I can always add you to the group and you be part of the group effectively so that you can acquire all the notes as required. So I've sent the notes for that explanation. You'll have them. Then the next definition I want to talk about this afternoon is what we call the thermoconductivity. Thermoconductivity. Or sometimes you call it coefficient of thermoconductivity. Coefficient of thermoconductivity. This one is normally given a letter K. This K is not for Kelvin, it's for coefficient of thermoconductivity. Now, as you go through those notes I've sent, as you write them down, in case you have a challenge, please don't hesitate to inbox me for further explanation. And also recall all the time, if you have a question, please you raise it. Now, all of us have seen buildings, and you've seen people constructing perimeter walls or a wall of a building, like this one. Walls are built like this. I think we have seen this. Now, we can get, this side can be the side where the sun is shining. Someone has a hand. Yeah, Precious, I'll send my number. Yes. Then you send me your name so that I can add you to the group. So I was saying, if the sun, when you look at your house at home, the side where the sun ends from, yeah, always that side, the wall is hotter. So if this is where the sun is shining, this side will be what? Hotter. This side will be cooler. Now what happens is, heat will have to transfer from here to the side where it's cooler. Why? Because heat always travels from a region of high concentration to a region of low concentration. Now, when you get that concept that it travels from high concentration to low concentration, and you have given you an example of the wall in a house, which wall is on the side where the sun sets from? Yeah? This is where it sets. Then heat can be transferred from the side where the sun sets to the side where the sun came from. Now, if you consider a slab of material thickness L, cross-sectional area capital A, having temperatures θ1 and θ2 at the end. So this is how my slab can look like. The slab can be in form of like a brick, a compact tube, so if this is my slab, this end can have temperature θ1. This side can have temperature θ2. And this is the cross-sectional area, capital A. Then the heat is being transferred in that direction, whereby Q is the heat, while Q over T the rate of flow of heat. Now, if you look at heat going in this direction, if heat is going in this direction, then clearly it means this temperature is hotter than this one. So it means θ1 is hotter than, greater than θ2. So that means the heat on this end, let me call this end P, and the heat on the end W. The heat on the end P is greater than the heat on the end W, because the temperature at P is θ1, which is greater than the temperature at W, which is θ2. Okay? So with that, we can as well talk about the rate of heat transfer. What does it state? The rate of the heat the rate of flow of the heat energy which is Q over T through the specimen will depend on the following factors. One, the cross-sectional area. Let me first explain some illustrations on this cross-sectional area. We have all seen welders. Those people who do go for metal workshops and play a role of building us beds, tables, chairs, which are metallic. The welders, when they do their welding, you've seen a lot of fire sparks coming from the welding part and the machine. Those welding sparks that come from the machine that is welding, they don't burn them. And you know the reason why? It is because the cross-section area of those fire sparks is very small. It is very small so they can easily lose the heat, right? Whereby, by the time they reach the person's skin, they have already cooled down. Okay? Now, the same applies also to absorption. When they are small, they take long to absorb heat, while a bigger body easily absorbs heat. That is why if you're cooking items, a big piece, for example, if you girls who are here and boys, I trust most of you have ever cooked anything with tomatoes. Try cutting small tomatoes and try cutting big tomatoes. The big tomatoes have a big cross-sectional area, so they can easily get ready than the small tomatoes. So that's the dependency of cross-sectional area on how heat can easily be transferred. So heat is transferred very easily to an item which is bigger in cross-sectional area than an item which is smaller. Why? The small substances that do not absorb heat at the same rate as the bigger substances. Then the second one. So there it means that the bigger the cross-section area, the faster the item assumes what? Heat energy. Or the faster the rate of flow of heat energy. If you look at this whiteboard and this phone is smaller than this board. This board will get heat very fast compared to this phone. So the rate of transfer of heat in the board is greater than the one on the phone. Reason? The phone is smaller, as we shall see. The second factor is temperature difference. Temperature difference. The temperature difference between the two surfaces, for example, it is θ1 minus θ2 for the slab we had here. The temperature difference here was θ1 minus θ2. What is the difference between the temperature here and the temperature there? For example, take this case. If the temperature here was 100 and the temperature here was 90, the temperature difference would be what? The temperature difference would be 10 degrees Celsius. But if the temperature here was 100 and the temperature here was 20, then the temperature difference would be 80 degrees Celsius. So heat would travel faster where it has a difference of 80, which is bigger. Why? There are so many regions where heat energy has not yet reached. While for the case of the 90, many regions have already acquired what? Heat. So very few atoms are in need of gaining a lot of what? Heat. But if the difference is big, it means that very many atoms of the slab want to acquire all the amount of heat that is there. So heat there travels faster because the temperature difference is big. Therefore, the bigger the temperature difference, the faster the rate at which heat will transfer or flow from one region to another. Then the third case. The third dependency, nature of the material. Nature of the material. Let me give a very good example. We all know very well what an egg looks like when you want to fry it. First of all, does the egg which has been fried and the egg which has been boiled, do they all take the same time to boil? No. It means the heat is not flowing into them at the same rate. This one which is being fried, the moment you put it on a frying pan, it's ready. When you turn it upside down, you just have to serve. While for the ones which are boiled, they have the outer shell. I don't remember its name. They have the outer shell. When you put them in water and you boil them, you first transfer heat to the shell. Then the shell will transfer heat to the liquid inside. Then the liquid inside will transfer heat to the yolk. Okay? And now all those processes will take longer. But now here, when it has been smashed already, there's a word they use for in English, how to make the eggs which are going to be omelette or Italian fried. You will have mixed all those items. You remove the shell, then you have that liquid. Is it the chalaza? I don't remember the name. Then you have the yolk. But now you put them together and they form a new precipitate, which when easily cooked, the rate at which heat transfers through it is higher than when you have it still in the shell. So that means that the material is different. The material of the egg, when it is on a frying pan, is different from the material when it has its shell combined with the liquid inside, combined with the yolk, and all of them are still in their original states. Another thing we can talk about is, you've seen carbonates. When you touch them, sometimes they gain heat. But when you have also been walking in the sun at the same time as the carbonate, when you touch your skin, it is not as hot as the carbonate. Means the nature of the materials is different. So the nature which is, for a carbonate, is the nature which is close to metals, and we already saw how metals transfer heat. Then your body skin is not the same as a metal. So there is no way you can have the same rate of heat transfer. So some materials have better, this is where we get what we call the coefficient of conductivity. Some materials have better coefficients of conductivity, others have worse coefficients of conductivity, meaning some are good conductors of heat, others are worse conductors of heat. Then the last one, the last dependency, is inverse of the distance. Inverse of the distance between the surfaces. This means that if I have this surface this side, I have this surface, and I have another surface here, then those two surfaces have a length between them, which length is L. Then the rate of heat transfer is inversely proportional to the length between the surfaces which have a temperature gradient. When I say they each have a temperature gradient, it means they have a temperature difference. Okay? So for that reason, we would get to the relationship which says the rate of heat transfer, which is Q over T, depends on 1, the cross-sectional area, 2, the temperature difference, and then 3, the inverse of the length between the surfaces that are at different temperatures. So thereby, if you remove the proportionality constant, we shall have Q over T is equal to K, in 2 brackets, theta 1 minus theta 2 times the cross-sectional area divided by L. So this is the relationship which defines the rate of heat flow or heat transfer in solids or in a conductor. Sometimes it's written like this. Sorry about that. The rain was so patient. But don't worry, I'm going to send the notes. So I was still saying that the rate of heat transfer can be defined by Ka of theta 1 minus theta 2 out of L, whereby this is the same as Ka change in temperature theta out of the length L. So it is the reason why I say that if you have a big surface area, it means that because it is directly proportional to area, it means that the bigger the surface area, the higher the rate of heat transfer. It means if you're cooking items with bigger pieces, they can easily get ready. And I've told you one live example you can test is to have a tomato cut longitudinally. I wish I had one here, rather than cutting them in small tubes. Those tomatoes cut in small tubes take longer to get ready because they take long to try to absorb the heat. The same application, if the tomato is like this, you better cut them longer like this to get ready than when you cut them like this to make those small tubes. Then if you're having a frying pan and you let your egg spread just around here, the egg takes longer to get ready. But the reason why you see those chapati guys spreading the egg all over, it's because they want the egg to get ready what? Faster. So they are increasing the rate of transfer of what? Of heat when they spread the egg. So that is why some of these items have to be cooked in big sizes rather than in small what? Small sizes. So with those illustrations, we can make K the subject. So this K is what I talked about, or is what our heading was talking about. K is the coefficient, is the constant known as the coefficient of thermal conductivity. Okay. Then the quantity of theta 1 minus theta 2 divided by L is what we call the temperature gradient. The temperature gradient. And the units for temperature gradient are Kelvin per meter. This is the SI unit for temperature gradient. Also, K is a constant. I've said it's already different for every material, which depends on the nature of the material. So that is the reason why every material has a different value of K, and that means every material has a different rate at which heat is transferred through it. That is the same reason why you cannot cook eggs for the same time you cook rice, for the same time you cook matoke, for the same time you cook a chapati, for the same time you cook spaghetti, for the same time you can cook porridge. All those different items have different coefficients of thermal conductivity. So if I want to derive the units for K, units and dimensions for K, Hope all of us had covered dimensions at school. From Q over T, because it's the first lesson in paper 1, mechanics, is equal to A, changing theta over L. When I make K the subject, I'll get rate of heat flow divided by K, and the temperature what? Gradient. If I want to get the dimensions of K, there is no K here. Rather, there is A. Therefore, dimensions of K shall be got from dimensions of Q over T out of dimensions of cross-sectional area times dimensions of temperature gradient. But one can also express them like this. Dimensions of rate of heat transfer times dimensions of L when L goes up over dimensions of cross-sectional area times dimensions of temperature change. This will give me energy is M L squared T power negative 2 times L for length over L squared for area times T for temperature. Dimensions for temperature are small t, because temperature is fundamental. Okay? So with that reason, we shall have, you lose 1 L here, you lose 1. You remain with 1 L up here, which will give us M L per T squared. This is going to be per small t. So these are the dimensions of K. Now, if they ask you for the SI units, yeah, unit of K, the units of K are Weber, Weber meters over meters squared times temperature, Kelvin. I can lose 1 meter, and this will give us Weber per meter per Kelvin as the SI unit of the thermal conductivity coefficient. So W is what? Is known as Weber. So those are the SI units of what? Of coefficient of thermal conductivity. So they can ask you to define. In physics, right from O level, the highest scored mark is a definition or a principle or a theorem or a law. The rest of the marks are got from hubs and the quarters in practicals. So you always have to endeavor to see that you know most of the definitions depending on the situation. Now, to start with, the definition I want to look at right now is the definition for K, which is the thermal conductivity. It can be defined as definition of K. It can be defined as the rate of heat flow. The rate of heat flow through a material of cross-section area of 1 meter squared and temperature gradient of 1 Kelvin per meter. Or sometimes you can define it as the rate of heat flow across opposite forces of a 1 meter cube of a material. Okay, sometimes you can say or, let me write it here, or is the rate of heat flow of across opposite faces of 1 meter cube of a material between which the temperature gradient is 1 Kelvin per meter. So both of those are definitions which we can look at to define K, which is the coefficient of thermal conductivity. Also, that one I promise I will send more write up on that so that you can summarize the notes and have better. Sorry, the network is being interfered by the rain, but I trust that since I've sent the write up, you'll be in a position to catch up with what we have to catch up with. I was about to come into what we call rate of heat flow in a lagged and unlagged bar. What does the word lagging mean? You putting on a cloth, you have lagged your skin. If your skin is bare, then we can say it's unlagged. So basically lagging would imply that something like a protective gear one can put on an item, either to prevent heat from escaping or to prevent external heat from coming in. We have seen these examples, one in flasks. Flasks have a lagging, which is the outer casing, which protects the flask from losing heat to the outside. So one end of the bar is put in a steam chest, while the other is kept cool by a current of water until when a steady state has been attained. For example, you get a bar, put it one side in what? In a steam chest. Then this other side, keep it cool by letting water run through on this side. So that water will be cooling it in one way or the other until when a steady state is attained. Yeah? That implies that the temperature will go on falling steadily. This temperature will be higher, but as heat travels to this side, it will find this cool region. So time comes when it becomes steady, and that means at that instant we shall have a uniform distribution of heat. Whereby we shall have what we call a steady rate of flow of heat. So heat will be flowing steadily from one region to another. Now, if it is lagged, it looks like this. So if it is lagged, we do this. This is what shows that it is lagged. So the piece of bar is inside here, which has heat flowing through it in that direction. So this side, maybe it was at 100 degrees Celsius. This way it was at unknown temperature, theta, at which maybe water was, because this side is where we have water. So we don't know that water, it was cool. So we don't know the temperature at which it actually was being cool. Now, in this case, when the rate of flow of heat is steady, and then you lag it, this is the lagging. Yeah. Then the rate of heat flow along the bar is constant. Why? Because there is no heat loss to the surrounding. So when we lag the material, we do not lose any heat to the surrounding. So if heat is not lost to the surrounding, it means the material has been lagged. So that means there will be a steady rate of heat flow throughout the entire bar. Why? Because it has been effectively lagged. Yeah. Then for an unlagged material, actually the graph for this one would be of this case. Straight line graph. Material attain a steady temperature. While for an unlagged material, you would find that that material would be like this. This material heat will be traveling anywhere at once. So the heat can move to the surrounding. Okay, this is length, not time. Then this one will have a graph like this one. So this is for the unlagged, the other one was lagged. So with this regard, you would see that the rate of heat flow decreases from a hot end to the cold end because there is heat loss to the surrounding. So this one, it is a curve which is in this shape, while for this first one, it was a straight line. The temperature gradient was non-falling, which is change in temperature over length is uniform. While here, change in temperature over length is non-what? Non-uniform. Why? Because the material is unlagged. So basically, that is the introduction of what we are calling heat transfer. And we have also discussed what we call the coefficient of thermal conductivity. Now, to introduce calculations of bricks and the like, I think the next lesson is what? Thursday. So if the next lesson is Thursday, so I will have to do that on Thursday and we start doing calculations. So please go through these notes I'm sending right now, write them down. They will be of help for you to go through the exercises and examples we are going to do. I'm also going to send the examples so that you copy them down when I come on Thursday or whatever day we shall have to meet again. It's probably Thursday or tomorrow afternoon. I'll just be in position to do the numbers so that we don't waste much time writing down the numbers. Otherwise, if you don't write the numbers, every time you come and write the numbers, they take some good hours, minutes. So to avoid that, I'm going to send the numbers, you copy them also. And by the time we meet, you're comfortable. So any questions before we can close the meeting? Those who are new, I've written mine. I sent you my number already. And I've added already one person to the group. I'm sending more notes there. So I wanted to know if someone has a question before I can end the meeting. I've also sent the numbers. I've also sent the numbers and people should be in position to try them out. No, you cannot try them out. You'll have to wait for me. It's just that I just want to write them down. Eh? Copy them and write them down. Okay, if no questions, let's end the meeting.